For today's lesson, we will be discussing about the chain rule of differentiation. So this is another technique that we can use in derivatives and finding derivatives of different functions. So before we proceed with our discussion about the chain rule, let's recall first what is composition of functions. So when we say composition of functions, this is an operation that involves two functions wherein a function is within another function. So if we can recall the composition functions, so we know that is f of g of x. So this is an example on how we denote composition of functions. So there are two functions, f of x and g of x, and g of x is within our function f of x. So when we say composition of functions, it's like you are substituting a function inside another function. Another way of writing composition of functions is like this: f circle g of x. Let's just try to write the composition of functions of these two functions that I have here. So f of x is sine of x, g of x is 6x. So if we want to do composition of functions, f circle g of x, so this will be sine of 6x. So instead of writing x, we substitute now the g of x to our function. So we now write 6x, sine of 6x. So again, imagine we have the two functions, sine of x, we have the 6x also, and then we put the 6x to our sine of x. That's why it becomes sine of 6x. So that's an example of a composition of functions. Another example, let's say we have e raised to x, and then we have the g of x, which is x plus 1 all over x minus 2. So if we will do again the composition of functions, so we have here e raised to, so instead of x, we will replace it with x plus 1 all over x plus 2, x minus 2. So we have x plus 1 all over x minus 2. So there. So that is now the function. Third one, let's say we have f of x, which is ln of x, and then we have the g of x, which is square root of x. So again, if we do composition of function, we will replace the x here in ln of x with the g of x, which is square root of x. So it now becomes ln of square root of x. So here in composition of functions, as you can see, we have two functions. We can classify them as the inner function and the outer function. So the inner function is the one that we substitute. So in this case, that is g of x. And the outer function is this one, which is ln of x, or our f of x. Now in derivatives, so we can also solve for the derivatives of these kinds of functions, or what we call as the composite functions. So how are we going to identify the derivative of a composite function? Let f and g be two differentiable functions. So the derivative of the composite function f circle g of x is given by the following formula. So we have here f circle g prime of x is equal to f prime of g of x times g prime of x. So this is what we also call as the chain rule. Okay, so this is the way on how we can get a derivative of a composite function. Again, we use a chain rule. In composite function, like what we saw a while ago in the previous examples, there is a function within a function, and we also have what we call as the inner function and the outer function. So you can think of this chain rule as like you are getting the derivative of the outer function, and then you multiply it to the derivative of the inner function. So you should identify which one is the inner function and which one is the outer function from the given. And then from there, we can now get the derivative. Again, for the chain rule, you get the derivative of the outer function or the whole function. And then, you have to identify the inner function and get its derivative as well. And then multiply at the end. So that is how we apply the chain rule. So to visualize everything, let's have some examples. So let's say we have here this h of x equals quantity of 4x plus 5 cube. Okay, so here, so this is the function given. So you have to check the structure of our function. So as you can see here, this whole expression is being raised to a certain power. And if we will try to separate this two, okay, so let's say we have here f of x and we have the g of x. So since this one is composite functions, we can try to separate the two. We can try to separate the two functions so that we can identify which one is the inner function, which one is the outer function. So in this case, so this is our whole function. A quantity is being raised to 3. So we can write it as x cubed. Okay, a quantity, which is, let's say, just x, is being raised to 3. That is the outer function. Now, how about the inner function? So that quantity that is being raised to 3 will be our inner function, which is this one, 4x plus 5. So that will be our g of x. So you can think of it as like this. So this is the structure of our function. So we have x cubed as the outer function. That is just a representation. A quantity is being raised to 3. And then, what is that quantity? So that quantity is our g of x, which is 4x plus 5. Okay? So from here, we're now able to identify what is the inner function, what is the outer function. So from here, how are we going to get the derivative? So you can rewrite this whole function. So what we will do is, the inner function, we can change this or represent it using u. This will be 4x plus 5. So that instead of writing 4x plus 5 here, we can now have u cubed. Okay? Which is now familiar to us. So it's like x cubed. So we can already get its derivative. But remember, u, its value is 4x plus 5. Okay? So we will now apply the chain rule here. So this is the whole function. This is the outer function now. And we have the inner function, which is 4x plus 5. So you have to remember that. So let's get the derivative. H prime of x is equal to. So from the chain rule, you have to get the derivative of the whole function or the outer function. So that will be d over du of u cubed. Then you have to multiply it with the derivative of the inner function. So the inner function here is the value of u, which is 4x plus 5. So derivative of 4x plus 5. Okay? And then just get the derivative. So this one, for u cube, you can already just use the power rule. So just get the exponent, you multiply to the base, and then subtract 1 so that you'll get the new exponent, which is 2. Okay? And then this one, get the derivative as well. So that is 4x plus 5, derivative is 4. And from here, you can just simply multiply the 2. So you have 12u squared. But remember, u is 4x plus 5. So you still have to substitute or bring it back into 4x plus 5. So 12, then 4x plus 5 squared. And then that's it. This is now the derivative of our function. And again, we used here the chain rule. So here, again, we try to identify first what is the form of our outer function and what is the form of the inner function. And then from there, you substitute the inner function with u, rewrite our original function, and then use the chain rule. This is just one way on how we can solve. We just use the u substitution. But actually, you can solve the chain rule without changing to u. But again, it's up to you now. What do you want to use? So let me just show you the process, how to do it. So let's say we have here again this one, h of x equals 4x plus 5 cubed. So you can just directly go and get a derivative without changing the u. So what you will do here is, you get the derivative of this whole function. So think of 4x plus 5 as 1. Let's say that is just x. So what you will do is you just have to apply the power rule. So you multiply. So you have 3. You copy the base, 4x plus 5. And then minus 1 to the exponent. So that is 2. Then multiply to the derivative of the inner function. So again, we know the inner function is 4x plus 5. So what's the derivative of 4x plus 5? The derivative is 4. And then you can just simply multiply. So you have 12 and then 4x plus 5 and then squared. And then that's it. You're able to get the same answer. So as long as you know which one is the inner function and what is the form of the outer function, so you can already solve for the derivative without changing the inner function to u. But if you think the first method is easier for you, then you can use it. Let's have another example. H of x equals sine of 2x. So again, first thing that you have to do is just to visualize first what do you think is the original, or what is the outer function and what is the inner function. So here we have sine of 2x. Usually what we have is the sine of x, cosine of x, so on and so forth. So that can be our outer function, sine of x. And what is our inner function? Our inner function is, so since in our outer function this one is x, but in the given it's 2x, that means our inner function is the 2x. And if you do composition of functions here, f of g of x, you just have to substitute 2x to the sine of x. So that's why we have sine of 2x here. So we can now again substitute u to 2x. So we can just change this, so this will become sine of u. Okay, and then let's apply now the chain rule. So you get, this is the whole function or the outer function, so you get the derivative of that, sine u, then multiply it to the derivative of your inner function, which is 2x. So 2x. The derivative of sine is cosine, and since the variable that we used here is u, so we just have to write cosine of u, times the derivative of 2x is 2. And then just multiply, so you have 2 cosine of u. And then last step is to replace u with 2x, since that's the original value. So 2 cosine of 2x. And then that's it. That is already the derivative of our function. Okay, let's have another example. So here we have h of x equals the square root of 3x squared minus 5. So from this one, again, we identify which one is the inner function, which one is the outer function. So here, we can say that 3x squared minus 5 is our inner function. So if you want, you can still write f of x equals and then g of x here, which is again 3x squared minus 5. Now if the inner function is 3x squared minus 5, what's the outer function? So the outer function may be square root of x. Okay? So square root of x, and if you replace it with 3x squared minus 5, which is our inner function, so you will get this one, h of x. Okay? So that means our inner function is 3x squared minus 5. So let's now replace it with u. So we now have here square root of u. Okay? And like what we always do whenever there's a square root or radical, we always change it into fractional exponents. So that is what we will do here also. So instead of square root of u, we will write it as u raised to 1/2. And then after that, let's now get the derivative. So we have here h prime of x. So since this is the outer function, and from the outer function there is still an inner function, we'll be using the chain rule. So get the derivative of our outer function, u raised to 1/2, times, then get the derivative of our inner function, which is the value of u, and that is 3x squared minus 5. So here we have u raised to 1/2. So we already encountered problem like this before. So this is like x raised to 1/2. So we will be applying the power rule. So multiply 1/2 to the base, and then subtract 1 from the exponent, so that's negative 1/2. And again, we don't want negative exponents, so we put it in the denominator and we put it back into its radical form. So that is 1 over 2 square root of u. So here, that's the derivative. So let's write 1 over 2 square root of u times, and then we have here 3x squared minus 5. So the derivative of that is 6x. So we apply the power rule as well. And then all you have to do is just to multiply. So you have 6x over 2 square root of u. Now, before we put it back into its original form, we can still simplify 6 and 2. So that will give us 3x over square root of u. And then from here, you can now substitute back the value of u. So 3x all over square root of 3x squared minus 5. And now this is our final answer. So this is now the derivative of our function. For our next example, let's have h of x equals x ln of x squared minus 1. So what you will do here is you have to look at the given function. So observe the function. You should identify that there are two terms here. First is our x, and the second one is ln of x squared minus 1. So that is how you do it. In the previous examples, there's only one term present, so we don't have any problem with that. But if in case there's something like this, there are more than one term present, so you have to identify them. So that is one clue that I can give you before you start answering, or before you start to think of what technique to use. The first thing that you have to do is to identify how many terms are there. And after you already identified how many terms are there, what operation exists between these terms that I identified. So in this case, we have x and it's being multiplied to ln of x squared minus 1. So it means that we will be applying the product rule. Okay? So you already know the terms. We already know the process or the technique that we're going to use. So we're going to use the product rule. Now, after that, you have to look at each term that you identified. So we have x. So we don't have any problem with that. It's just x. But for the second term, which is ln of x squared minus 1, you will notice here that there is a function within a function. So ln is already a function, and then x squared minus 1 is still another function. Okay, so you will notice that in the second term, we have now composite functions. Okay, so here we can identify that x squared minus 1 is our inner term or inner function. Okay, again, why do we have u as x squared minus 1? Because it is our inner function. Aside from the function ln, we still have a function inside of it, which is x squared minus 1. Okay, so it means that we will also be applying the chain rule. Okay, so we will be applying the product rule, we will be applying the chain rule, and we're able to identify which among the terms here should we apply the chain rule. So it's in the second term. So what you can do here is you can rewrite your function, so it now becomes x ln of u. So here you know that in this term ln of u, you will be using chain rule. So here we have u and v, just like the usual product rule that we know. So let's write here. So u dv, so u, that's the first term, times the derivative of our second term. Oh, let's write here d over du, times derivative of the second term plus v du, the second term, times the derivative of our first term, which is x. Okay, and then from here, let's now get the derivative. So we have x, so just write x. Nothing special, nothing to do about it. Now for ln of u, since this one is a composite function, as we already identified before we start, so we will be using the chain rule. So what you will do is, let's try to make or write a bracket here, like that. And then, let's apply the chain rule. You get the derivative of the whole function, or derivative of the outer function, which is in this case is ln of u. Then you multiply it with the derivative of the inner function, which is in this case is x squared minus 1. Okay, so this one, the green font here, that means we are applying the chain rule. Plus, here it's just ln of u, and then the derivative of x is 1. And then let's just simplify this. So we have x again. And then let's simplify this one, the one inside the parentheses or the bracket. So the derivative of ln of u. So just think of u as x. So ln of x. What's the derivative of ln of x? That's 1 over x. But since the variable is u, so let's just write 1 over u. Times, and then this one, the derivative of x squared minus 1 is 2x, using the power rule. And then just write the remaining terms. So ln of u times 1, that is just ln of u. And then from here, let's now simplify. So I have x, and then this is just, you just have to multiply. So it's 2x over u plus ln of u. And then you multiply now x with 2x. So to further simplify, so that will be 2x squared all over u plus ln of u. Now since we cannot simplify it anymore, so let's now substitute. So h prime of x is equal to, so do not forget to substitute back the u variable with the one that you identified a while ago. So 2x squared all over x squared minus 1 plus ln of x squared minus 1. And then that's it. This is now the derivative of our function. So here we use the product rule, and then we also apply the chain rule. Another example, so here we have h of x equals logarithm of 2x plus 5 base 4 all over x raised to 4 plus 1. So again, how are we going to start solving this? So remember the steps that I mentioned a while ago. First, you identify what are the terms that you can see in this given problem, and what operation involves between these terms that you identified. So here, as you can see, we have two set of terms. So we have logarithm, and then we have in the denominator x raised to 4 plus 1, and they are being separated by division. So it means that I have to use the quotient rule. So I have to write here high and then low. So again, I will be using the quotient rule since there are two terms involved and they are separated by division. And then after that, you have to check each terms that you identified. So you check the numerator, you check the denominator. Maybe we need to still do something about them. So for the denominator, it's x raised to 4 plus 1. So nothing so special, it's just a simple function. But for the numerator, we have logarithm of base 4, and at the same time, within that logarithm, we still have a function of 2x plus 5. So that means the numerator is a composite function. And if it's a composite function, that means we have to identify the inner function, and that is 2x plus 5. So u is equal to 2x plus 5. Again, the numerator is a logarithmic function, and within that logarithmic function, there is still a function inside of it, which is the 2x plus 5. So that will be our inner function right there. So we set that as our u. And then what we will do is we will have to rewrite this whole thing. So let's just write logarithm of u base 4 all over x raised to 4 plus 1. And then we will now be applying our quotient rule, the low d high minus high d low. So let's write here, h prime of x is equal to low d high, low x raised to 4 plus 1, the derivative of high, so that is, oh, by the way, this one should be u, d over du. Let's erase that. Okay, and then this one is a logarithm of u base 4. Low d high minus high d low, high d low, there, all over low squared. So x raised to 4 plus 1 squared. And then from here, let's now get the derivative. So we have x raised to 4 plus 1, x raised to 4 plus 1 as is. And then here, we have to get the derivative of the logarithm. And here, as you can see, it is a composite function, and we have to use the chain rule here. So like what we did a while ago, let's place a bracket to separate this process from the other derivatives. So you get the derivative of the outer function, logarithm of u base 4, get the derivative of the outer function times the derivative of the inner function, which is this one, 2x plus 5. Okay, and then there. And then let's write the remaining terms here, minus, so logarithm of u base 4 as is, and then we have, this is the derivative, so the derivative of this will be 4x cubed all over x raised to 4 plus 1 squared. Okay, and then all we need to do next is just to solve for the derivative. So let's just write here again. So what we will do here is to simplify. So let's get the derivatives. So let's have x raised to 4 plus 1. And then for this one, logarithm of u base 4. So think of it as like logarithm of x base 4. So to get the logarithm, so to get the derivative of a logarithmic function, so that is 1 over x ln of a. Okay, but since the variable that we use here is u, so that will be 1 over u ln of a, and a is equal to 4. So that's the derivative. And then you multiply it with the derivative of 2x plus 5, so the derivative of that is 2. And then this one, we can just place 4x cubed in front. And then let's multiply the logarithm of u base 4. Okay, all over the denominator. And then let's simplify this. So what we will have is x raised to 4 plus 1. And then this one will be 2 over u ln of 4 minus, and then I have 4x cubed logarithm of u base 4 all over the denominator, which is x raised to 4 plus 1 squared. Now, if you will look at this function, you will see that there is a fraction in the numerator. So it becomes a complex fraction now. There's a fraction within a fraction. So we have to simplify that. Now, instead of getting the reciprocal of our denominator and then multiplying it to the whole function, what we will do is we can actually think of a term that we can multiply to both the numerator and denominator so that we can easily cancel the denominator, and that is the denominator itself. So u ln of 4. So you just have to multiply the numerator and the denominator by u ln of 4. So it's like you're multiplying by 1, but you just have to, but you just write it in a different way, which is u ln of 4. Why u ln of 4? Because again, we have to cancel the denominator here. So if we multiply this, so if we distribute this to the numerator, we can already cancel out here. So the problem is already solved. So what I will do is, again, you multiply, so this will be cancelled, so you will be left with x raised to 4 plus 1 times 2 minus, and then here you just have to multiply. So we can write here 4x cubed logarithm of u base 4 times, and then this one, u ln of 4. And then all over, so you multiply here also, x raised to 4 plus 1, and then squared times u ln of 4. And then that's it. The last step that we have to do is just to write it back into its original form, wherein we substitute all the u variable with 2x plus 5. So let's just write here the final answer. Wait, let's use this one. So the final answer will be, let's try to fit here the final answer. So we have, let's multiply x raised to 4 plus 1 and 2. So that will be 2x raised to 4 plus 2 minus, and then I have the 4x cubed logarithm of, and then I have 2x plus 5 base 4 times 2x plus 5 ln of 4. Again, what I'm doing here is just substituting back 2x plus 5 to our function all over, and then we have x raised to 4 plus 1 squared times 2x plus 5 ln of 4. And then that's it. This is now our final answer. So there. So here we're able to use the quotient rule, and at the same time we're able to use the chain rule.